Howdy! In this mini lecture, we will discuss oil sands and oil shale, refining oil, use of coal fossil fuels, and peak oil. The student learning objectives of this mini lecture are describe the Keystone XL pipeline project and its significance, classify oil sands and oil shale, summarize how oil shale is extracted, describe the process of oil refining, summarize the uses of coal, outline the benefits of natural gas, identify the top consumer of oil, coal, and natural gas, distinguish between proven recoverable reserves and reserve to production ratio, and summarize the issues of peak oil, which complicates the prediction of peak oil and the societal impacts of reaching peak oil. A lesser known type of fossil fuel are oil sands and oil shale. Recall I mentioned earlier that Canada and Venezuela both have a great deal of oil sands. Specifically, Canada has the third largest proven oil reserves, but these reserves are oil sands. Oil sands, also known as tar sands, are layers of sand or clay saturated with the viscous tarry type of petroleum called bitumen. The bitumen can vary between 1 and 20% in the clay and sand. Bitumen is a form of petroleum that is rich in carbon but poor in hydrogen. Oil sands are essentially crude oil deposits that have been degraded by water erosion and bacterial decomposition. Some people think the oil sands of Canada are the answer to continuing our current fossil fuel-based lifestyle amid dwindling supplies of oil. Others think that extracting the oil from oil sands is an appalling pollution that perpetuates our dependence of fossil fuels and is an even greater threat to Earth's climate. Consider this fact as you contemplate where you stand on this issue. The EROI for oil sands is estimated to be between 1.5 to 1 and 9 to 1. With most estimates being between 3 to 1 and 5 to 1. Compare that to the EROI of oil, which is currently about 11 to 1, hydropower, which is 10 to 1, and wind, which is 23 to 1. What does this tell you about oil sands? In order to get to the oil sands, the boreal forest under which they sit must be cleared and the area is strip mined. The sands are mixed with hot water and chemicals, creating toxic wastewater. The Canadian oil sands produce 1.7 million barrels of oil per day. We, the United States, are the major purchaser of this oil. This is a major national debate over the pipeline that transports this oil from Canada to the U.S. This pipeline is called the Keystone Pipeline. The existing pipeline has limited capacity, and for many years, the TransCanada Corporation has pushed to build an extension, called the Keystone XL Extension, to deliver more oil at a faster pace to ports as far as south as Texas. As with most issues, the Keystone XL Extension has staunch proponents and opponents. Among other things, the proponents want the jobs the pipeline would create. The opponents dislike the destruction of the boreal forests in Canada and the potential for an oil spill over the Ogallala Aquifer in the United States. Oil shale is sedimentary rock that is filled with kerogen. Oil shale can be processed to produce shale oil, which is a type of petroleum. Oil shale forms when kerogen was not buried deeply enough or was not subjected to enough heat and pressure. It's important to note that oil shale is not related to shale gas. Shale gas is another name of natural gas and is generally extracted using hydraulic fracking. It is estimated that 65% of the world's shale resources are located in the northwestern Colorado, northeastern Utah, and southwestern Wyoming. Oil from oil sands are extracted using one of two processes. If oil sand deposits are near the surface, they are extracted using strip mining. For deep oil sand deposits, deep injection wells are drilled and steam and solvents are injected to liquefy and isolate bitumen in place and pump it out. Once oil sands are extracted, they need to be processed to upgrade the oil to valuable synthetic crude oil, called Syncrude. Oil shale is extracted using strip mines or subsurface mines. Once extracted, oil shale can be burned directly like coal or can be baked in the presence of hydrogen and in absence of air to extract liquid petroleum. The reason why crude oil has its name is that in its natural and purest form, this form of oil has very little use to us. Crude oil must be refined to get the various fuels we use, such as gasoline, kerosene, and diesel. The process of refining crude oil produces a variety of fuels. Crude oil is a complex mix of hydrocarbons. Different petroleum products can be made if the hydrocarbons are separated. The hydrocarbons have carbon chains of different lengths. The length of the chain determines the molecule's properties and use. The simplest way to look at this is that the longer the chain is, the more energy the fuel has. Refining is the separation of hydrocarbons based off of size and chemically transforming them to create specialized fuels for many uses. In addition to producing fuels, refining can also produce lubricating oils, asphalt, and plastic precursors. Crude oil is refined by boiling it. As it is boiled, the hydrocarbons volatilize and float upward through the distillation column. The image on the right shows the different type of crude oil products produced at various temperatures, and the barrel on the bottom left shows the percentages of each major category of product that is typically generated from a barrel of crude oil. It is important to note that although there may be more fossil fuel deposits, they are not all feasible to extract. However, technology advances are enabling companies to access some of the more difficult to extract fossil fuels. This means that with technology, the amount that is technically recoverable increases. While technology limits what can be extracted, it is economics that determines how much will be extracted. Some fuel is so hard to extract that it is just not worth the cost. As prices rise, however, economically recoverable amounts approach technically recoverable amounts. This leads us to the term proven recoverable reserve. This is the amount of oil or any other fossil fuel that is technically and economically feasible to remove under current conditions. Fossil fuels have many uses. Cultures have used fossil fuels for centuries. Ancient China, the Roman Empire, and the Hopi Nation are all known to have used coal. Coal helped drive the Industrial Revolution. One of its first uses in this revolution was to fuel furnaces to produce steam. Coal is used to generate electricity. We burn coal to convert water to steam. The steam turns the turbine, which in turn generates electricity. This can be seen in this figure of a coal-fired power plant. We now have clean coal technologies that help to filter out the pollutants from the combustion process. Clean coal processes also collect toxic ash residue and dispose it at a hazardous waste disposal site. Natural gas is versatile and clean burning fuel. Per unit energy produced, it emits half as much CO2 as coal and two-thirds as much as oil, meaning that natural gas burns much cleaner than coal. Natural gas is used to generate electricity, heat homes, and cook food. You may have heard of liquefied natural gas, or LNG. LNG is gas converted to liquid at low temperatures. Because it produces less carbon emissions than coal, natural gas is viewed as a bridge fuel, because it could serve as the bridge for the switch from a fossil fuel-based economy to a renewable energy-based economy. The United States and Russia lead the world in production and consumption of natural gas. In this table, you see that China is the primary producer and consumer of coal. Coal provides 40% of the United States' electrical generating capacity. Our modern fossil fuel-based economy began in Titusville, Pennsylvania, when the world's first oil well was drilled in 1859. Today, the world produces and uses nearly 200 gallons of oil each year for each person on the planet. Oil is mostly used for transportation. However, technology has advanced to the point that we now are able to use oil to make a wide variety of products, including plastics, lubricants, fabrics, and pharmaceuticals. Though the U.S. accounts for only 4.4% of the world's population, it consumes one-fifth of the world's oil. We can expect difficult decisions and conflicts in the near future regarding fossil fuel resources as the industrialization in China and India is increasingly driving world demand. As has been mentioned before, fossil fuels can be refined to create petroleum-based products. Look around your room or any place you spend time indoors and you'll see petroleum products everywhere. They are in the fabrics we wear, the materials we consume, for example, waxes on food, the pharmaceuticals we take, and other products we use every day. We are gradually depleting our fossil fuel reserves. Current estimates indicate that there is slightly more than 1 trillion barrels of proven conventional reserves left. If you add the oil sands of Canada and Venezuela to these reserves, we can get to 1.6 barrels or more. We have used up to 1.1 trillion barrels of oil, almost half of our reserves. The reserves to production ratio, or R/P ratio, is the amount of total remaining reserves divided by the annual rate of production, for example, extraction and processing. At current levels of production, which is 30 million barrels per year, we have about 54 years of oil left. Using the R divided by P ratio, natural gas reserves would last 64 more years, and coal would last 112 more years. The true number of years left for each fuel may be different from that which is predicted by the R/P ratio. It may be less since our demand and production have been increasing. Alternatively, it may be more as technology and price increase and we find more proven reserves. For example, mining of oil sands has increased reserves. But here's the kicker. We will face a crisis not when we run out of oil, but when the rate of production comes to a peak and begins to decline. In general, production of a resource declines once reserves are depleted halfway. Past the peak, if demand holds constant while production declines, a shortage occurs. This gets us to the key concept of peak oil, which is when the rate of oil production peaks and then declines. In 1956, Shell geologist M. King Hubbard predicted that crude oil production in the U.S. would peak around 1970. This prediction is called Hubbard's peak, and as you can see from the graph on the top of this slide, Hubbard's prediction proved to be accurate. U.S. oil production peaked in 1970. Since then, Alaska, the Gulf of Mexico, and secondary extraction has declined. The curve shifts to the right as more oil is discovered. Today, U.S. oil production is spiking upward as deep offshore drilling and fracking make new deposits accessible. Hubbard also analyzed data and predicted peak global oil production in 1995. As you can see from the graph on the lower portion of this slide, global oil production is still growing. However, much of this growth is due to using advanced technology to extract alternative oil reserves, such as oil from tar sands, deep water, or tight formations. So while oil production is still growing at the moment, many scientists predict peak production in the next decade. This is due in part to the fact that discoveries of new oil fields peaked 30 to 40 years ago. In summary, we are using more oil than we are discovering. Each discovery of new oil sources delays the peak by increasing proven reserves. Some analysts believe we will continuously find new sources. Such people are often referred to as cornucopians. Others believe that our supplies are dwindling and that we are approaching or have already reached peak oil. These people are often referred to as peakists. However, predicting the exact date of peak oil is very difficult due to a variety of complicated factors. Richard Heinberg wrote the book Snake Oil: How Fracking's False Promise of Plenty Imperils Our Future, and in it he distills down data from a variety of national agencies and peer-reviewed studies to discuss the true nature and depth of fossil fuel dependency problems. He describes 4 things that complicate the prediction of peak oil. These are: number 1, there is a difference between reserves and resources. Reserves are defined as the total fossil fuel endowment that is extractable at realistic market prices and with current technology. Resources, however, are the total fossil fuel endowment. Therefore, you can see that although there may be more resources available, actually locating, extracting, and processing them may be cost prohibitive, or we may lack the technology to do so. Number 2, new discoveries such as very deep resources. However, data indicates that on average, the oil industry finds 1 barrel of oil for every 4 to 5 we use. The global peak rate of discovery occurred in about 1960 and has been declining since. Number 3, wildcards such as politics, technology, and the economy can complicate this prediction. Number 4, the International Energy Agency definition of oil includes natural gas liquids. In addition, some countries are a bit loose as to what they define as domestic oil. Sometimes they include imported oil in their calculation, which obviously will skew the data. Furthermore, some agencies include biofuel, which is made from agricultural products, in their definition of oil. This gets even more complicated. Companies and governments do not disclose their amount of oil supply. There is disagreement among geologists about reserves. The U.S. Geological Survey estimated twice the proven oil reserves as earlier estimates. However, one thing we do know is that peak production will occur and our lives will be profoundly affected. Experts studying peak oil indicate that the actual peak of world oil production will probably occur over several years, and the decline following the peak will continue for decades. So what are some of the impacts of passing peak oil without having developed renewable energy sources? Number 1, we are expected to experience the long emergency, which is when we lack cheap oil to transport goods. Consequently, our economies could collapse and become localized. Number 2, large cities could not be supported without urban agriculture. Number 3, fewer petroleum-based fertilizers and pesticides would mean increase in hunger. Number 4, suburbs will be hit hard due to reliance on cars. More optimistic observers argue that as supplies dwindle, conservation and alternative energies will kick in and we will be saved from major disruptions. If this subject of peak oil interests you, I would recommend you read Richard Heinberg's book, Snake Oil: How Fracking's False Promise of Plenty Imperils Our Future, or his other book, Peak Everything: Waking Up the Centuries of Decline. That concludes this mini lecture on oil shale, oil sands, refining oil, use of coal fossil fuels, and peak oil. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline. Thanks and gig 'em!